Good evening to everyone. I welcome all of you to the 91st lecture in the lecture series in Nonlinear Dynamics conducted by the Department of Nonlinear Dynamics, Bharathidasan University, with the support from RUSA 2.0. It is my pleasure to introduce today's speaker, Professor Surajit Sen. Professor Sen did his PhD honors in Presidency College, Calcutta, and carried out his PhD in the University of Georgia and obtained his degree in the year 1989. He carried out his postdoctoral work at the University of Minnesota and at Michigan State University. He joined State University of New York, Buffalo in the year 1993, where he is a professor now since 2006. He is presently on leave as a distinguished visiting professor at the Indian Institute of Technology in Jodhpur in the Dar Desert of Western Rajasthan, where he is trying to study desert ecosystems. He is a fellow of American Physical Society from 2008, American Association for the Advancement of Science in 2012, and was a Fulbright Nehru Fellow in India 2017 and 18. He served as a Jefferson Science Fellow of the US National Academies in the year 2020-2021. Also, he was a senior science advisor to the US Agency for International Development in Washington, DC, during the same period. He is the member of American Physical Society and a lifetime member of American Chapter of Indian Physics Association. He has several notable publications in his area of expertise and also 6 patents. He has given several lectures and talks in many conferences across the world. With this short introduction, now I invite Professor Sen to deliver his lecture. Over to you, Professor.
Thank you so much for that introduction. It's a real joy. I can't tell you how excited I am. Let me share my screen and let me know if it's working okay, because I can't see anything once I share the screen.
Yes.
Okay.
Yes.
Okay, thank you. So around 1938 or so, Abraham Flexner, who was a very influential figure in America at the time, he was a doctor, and he was also quite a well-known intellectual with a lot of political influence. He wrote a book called an essay called Usefulness of Useless Knowledge. And I'd read out the opening part of it. Is it not a curious fact that in a world steeped in irrational hatreds, which threaten civilization itself, men and women, old and young, detach themselves wholly or partly from the angry current of daily life to devote themselves to the cultivation of beauty, to the extension of knowledge, to the cure of disease, to the amelioration of suffering, just as though fanatics were not simultaneously engaged in spreading pain, ugliness, and suffering. Flexner went on to be one of the founders of the Institute for Advanced Study in Princeton. And his influence shaped the modern medical curriculum that's practiced world over. Why am I saying this? I'm saying this because there is an interesting point here. In the modern world, there is great emphasis on making knowledge, generation of knowledge useful for society, as it should be. But you can't just make generation of knowledge useful for society by saying so or by planning so. Basic knowledge, what may seem as useless stuff or more or less useless stuff, turns out to be extremely important as well. And without that base plate, it's very difficult for practical knowledge to develop. So that's the reason why I want to make this brief statement regarding Abraham Flexner. Let me come to my talk. So the talk is about different stuff here, in keeping with Flexner's spirit, about sand, which is everywhere, about nonlinear dynamics, which this audience is an expert in, and metamaterials to some degree. I may not touch so much on metamaterials because it comes at the very last stage of my talk, and it's a fairly it has a lot of stuff in it, so I may not be able to get to everything. I'll talk about nonlinear waves, the history of it, at least to the extent I know. The Fermi-Pastor-Ulam-Singu problem, which is a very important problem, goes back to Fermi in 1954-55, when he wanted to study a chain of nonlinear oscillators and ran into huge surprises. And Stanislaw Ulam and John Pasta, who were involved with him, those are the three people here. Ulam is on the right, and Pasta is in the middle, and Fermi obviously is on the left. Fermi passed away around this time. He had cancer. He died very young. So much of this work happened actually post Fermi's passing. And the work continues. This particular system turned out to be so enigmatic that people still work on it. And lots of papers are published, and important papers, I should say. Then I'll switch gears a bit. I'll talk about nuclear reactor walls, the Newton's pendulum, which is a bunch of hanging pendula that you surely have seen, and the physics of sand and the nonlinear dynamics of sandy systems connected with the real world and with the observations. There are many characters here. I told you about Fermi, Pasta, and Ulam. The computations were done by Singu, and that's the lady out there. She's in her late 80s, early 90s now. She's still active. She's still alive. She's still doing well. Then you see Rufo, who did some major contributions. I won't be able to touch upon Rufo's work so much. And then you also see Miguel Honorato and Ilvov, who are these people here. They did some fascinating work on validating Fermi-Pastor-Ulam's work. The work on the nuclear reactor walls, pendulums, and granular materials was begun by this gentleman here, Vitaly Nesterenko. Vitaly is now a professor at University of California at San Diego. And he's one of the founding fathers of the area that we commonly refer to as nonlinear dynamics in granular materials. And some of the interesting work that I'll touch upon was done by my former student, now a scientist at Applied Biosciences on the bottom right. This is Michel Zaborski, who was one of my partners in this work quite a while ago now. And here are some nice pictures of Newton and Galileo before Newton, who laid the foundations of what Newton did, which shaped much of what we have done in the spirit of the historical foundations. So nonlinear wave studies, as far as I could tell, began pretty much in the 1400s, and this primarily began because the ships that came from Europe to essentially plunder Africa and the Americas and India and so on, and teach Christianity and find gold and buy spices and do some good stuff, all kinds of bad stuff. Many of these ships were actually sinking in the course of their journeys. And the reason why these ships were sinking was because the ships were not built for the kind of waves that were encountered in the seas. And thus people became aware of what we commonly or generically call as rogue waves. And so the study of these kind of large nonlinear waves began with all kinds of people getting involved. And here is a rough list. Well, first is a picture of a bad wave that can sink you. But more importantly, can you see the picture?
Yes, sir. Yes.
Okay. And this is, by the way, a wall of a rogue wave. A rogue wave is not always just a thing that pops up and goes away. Here you can see a wall coming in. And there are many areas that are famous for rogue waves. They can be quite localized in the seas. And that's partly because of the underwater geometry and the wave conditions that come in. This particular one is on the right is the Agulhas current driven rogue wave that knocked off a good part of a ship, as you can see. And this area is just around the east of Africa towards South Africa, towards the Horn of Africa. That area is very bad. Anyway, moving on, the European monarchs at the time, they essentially tried to attract attention of many of the well-known scholars of the period. You can see De Benedetti, you can see Huygens, Newton, Taylor, Euler, Lagrange, Laplace, Fourier, Airy, Stokes, Earnshaw, Businesque. The name goes on, right? And as you can see, the picture is that a lot of these very, very important figures, they got engaged in studying book waves or nonlinear waves, monster waves. Now, just to give you a sense of it, in case you probably know this, normal ships are built for about 45, 50 feet waves. That's what ships are built for, including the battleships, the destroyers, and all of that. But these waves can easily get up to 100 feet. So they're a threat for everyone. It's not like you can build a big enough ship, and they are not there anymore. So first, the simple stuff. We know what a wave equation is like, 1D, 3D, as I point out here. And then just to show a few of the nonlinear wave equations that are solvable. For example, you have the Sine-Gordon equation, which is basically a wave equation with the sinusoidal term. The KdV equation, which historically developed as an outcome of this effort from pretty old times, late 1800s, 1895. The KdV equation actually came after many steps. So the history of evolution of that is very interesting. Often not things that we study. The cubic Schrödinger equation, or the nonlinear Schrödinger equation, is a very important equation, we know, often studied in the context of rogue waves and solitons and so on. And on the top right, actually you have a rogue wave as seen from the satellite, which is essentially passing through. And this is typically how it looks like from the satellites. There is a fair amount of satellite imagery on rogue waves, from what I understand right now. So when you look at normal integrable equations, nonlinear equations, which typically tend to show soliton behavior, from what I understand, essentially the solitons, two opposing solitons pass through each other obviously with a little bit of slowdown just during passing, which is the phase change factor. And that's what I've tried to quickly lay down here from the work of Morikazu Toda. He introduced the exponentially interacting lattice. The potential is given here, where R is the interparticle distance, and you can write down the equation. And this one turns out to be solvable, integrable, hence. And Toda solved it, and this is one example where soliton crossing can be studied. So why am I saying this? I'm saying this just to lay down the history a little bit. Then came, if you will, at least in my head, the very important problem of Fermi, Pasto-Ulam, and Singo. This paper was never published. This was actually a Los Alamos report from 1955 when Fermi passed away. I think in late 54 he passed away. And basically, they took a linear chain, masses connected by springs. And in one case, you had a quadratic term of the spring and a cubic term, which was the nonlinear term. That's equation 1 here. And then you have a case where you have a quadratic term and you have a quartic term, which is the second equation here. And this, of course, is the equation of motion. So the potential is not what you see, but you see the forces. So you have a linear term in the forces, as in Hooke's law. And then you have a quadratic term, which comes from the cubic term in the potential. And here you have a quartic term going down to a cubic term because you're writing a force equation. They studied the system with 64 particles, and they found some very unexpected behavior. Now, these were all studied numerically, I should emphasize, because it's not possible to do them analytically. At least largely, it's not possible, at least in the discrete version of it. And They were computed in this Maniac 1 machine at the time. So it was a huge supercomputer of those days, and Singhu was the one who was doing the calculations. Her name was ironically left out of this report in those days, but people have had better sense in time and put her name back in, as it should be. So this numerical calculation was done in the following way, where suppose you didn't have the nonlinear term at all. Then you introduce some modes, because then the problem will have normal modes. You can think of the dynamics in terms of normal modes. Then you can introduce some modes as the initial condition and see what the nonlinear term does to these modes. So Fermi's expectation was that that the nonlinear term will allow for mode mixing. And the mode mixing would eventually rapidly lead for the system to reach an equilibrium state. That was Fermi's expectation, which actually turns out to be largely correct. That's exactly more or less what was found, but with some provisos. So first of all, when you simulate the system out, it turns out that the modes don't really tend to mix. So in this case, I think the one on the left is the cubic system, one on the right is the quartic system, if I'm not mistaken. Either way, it doesn't matter. The point is that these modes, you can see the first mode that was introduced tends to recur more or less with very tiny energy change. Similarly, all these modes tend to recur. Had they been mixing, they wouldn't have recurred, right? Because the energy from one mode would have substantially been moving to other modes. And over some range of simulations, you would expect the modes to get mixed up, some kind of equipartition to set in. That was not what they saw. It's not that the modes didn't mix at all, though. When they ran it long enough, they saw some mode mixing, but it's very small. Now, given the fact that this peculiar behavior was observed, a continuum picture was introduced, and that was done about 10 years later by Zabusky and Kruskal. They constructed essentially an integrable description of the FPU system with a cubic term, and that looked like a KdV equation, and hence that naturally showed soliton behavior, meaning that an energy pulse that doesn't disperse actually moves through the system or has a tendency to move through the system under the right conditions, of course. So we were learning about the system. This was about 17, 18 years ago. We had been working on Hertz systems, and we came into the Fermi-Pastor-Ulam system to study, which was a more complex system in the way I see it than the Hertz system. I'll talk about the Hertz system shortly. So we took a chain, in this case, a 100-particle chain, mass spring chain, quartic nonlinearity. We turned off the quadratic term completely, so it was completely quartic springs that connected the masses. And we introduced a single delta function velocity perturbation to one particle, in this case, particle 75. And it turns out that when you do that, the dynamic starts off by these propagating waves with some trailing tail. One is a compression pulse, the other is a dilation pulse. The chain had fixed boundaries. So the pulse would go and reflect, and then they would interact. And we wanted to see what the interactions would do. And what we found is that the interactions led eventually not quite to equilibrium, but to a weird phase that lasted a very, very long time. And at the time, we called it, for the lack of a better name, quasi-equilibrium. So the system looks and feels like equilibrium, but it's not equipartitioned. Okay. So in other words, initial condition information is lost. If you look at the velocity distribution of the particles, you would see a Gaussian profile. So in other words, that would mean that central limit theorem is at play. All velocities are represented. However, equipartitioning has a different meaning. It's a more strong condition. It says that every particle on average has the same energy. But that was not the case here. If you took the average, you found that each particle's energies fluctuated wildly. And this was what we thought was the hallmark of quasi-equilibrium. I had seen this quasi-equilibrium behavior in the Hertz system, which I'll talk about shortly. So it was very exciting to see it in this system. And we had written a paper on that already, on this peculiar phase in 2004, which is not very different, more general, but not very different from the current thinking about pre-thermalization that you often see in the literature. So our paper in 2004 was actually the first to bring up this issue from what I know. Moving on to something very different. So I just gave you a sense, a recollection, if you will, of the Fermi-Pascal system and that piece. But now I'll switch gears to something much simpler, as it turns out. So long ago, this was back in the early 80s or so, the Russians in their nuclear reactors, they felt that the nuclear reactor walls could be better at handling any kind of vibrations or any kind of perturbations, if you will, if the insides of the reactor walls had a thick layer of sand, something which is seen as absorptive, energy absorptive. And that's what they did. And once they did that, it turned out that the reactor walls actually became more prone to damage. They started to develop cracks. And so this was very mystifying. And Vitaly Nesterenko, he's both a physicist and a mathematician, and also is an engineering physicist plus a mathematician. He's a jack of all trades in the game. Vitaly was head of the Vrientov Institute in Siberia, in Novosibirsk. And Vitaly was asked to look at this problem to figure out what was going on. And being basically a physicist, Vitaly rigged up an experiment, and that's the experiment I show you here. He took an a quartz tube, a glass tube basically, and he put in these steel balls, perfectly aligned. He put a pressure gauge on the left and a striker on the right. So So the idea was that he hit this right side with the striker, just a hit, just a perturbation, if you will, like a delta function perturbation, not quite, but similar. And then he wanted to see what happened to the pressure gauge, how this very simple alignment of elastic balls, granular spheres, would transmit the energy. And it turns out that it was a fascinating problem that he ran into. And this was published in his first paper that appeared in Russian in 1983, but appeared in English, the translated Journal of Applied Mechanics and Technical Physics in those days, in 1984. You can find this paper. It's a very nice paper, short paper. Doesn't look like a very important paper at first sight, but turned out to be very important. So basically what Vitaly saw, which I don't show here, let me summarize, is that once he put the striker hit in, he actually saw one single blip of a pressure pulse at the other end. That's it. There are no other ripples, no other real dynamics going on, just a pressure blip. And that told him that this was most likely a solitary wave carrying system. I use the word solitary wave purposefully as opposed to a soliton. He called it a soliton, but it's better to call it a solitary wave. I'll tell you why, the distinction in due course. So let's go back to this contact between the grains very briefly. When Heinrich Hertz was 21 years old, and the year was 1881, he made a very important observation, and he wrote up this paper. Again, this paper is actually something that you can find online by Googling. It's written in German, but you can follow the equations. In this paper, what he showed is that if you have two elastic spheres, let's say of radius R1 and R2, and let's say they barely touch each other, and now you compress them, you squeeze them together. If you do that, then what would happen is that a circular, sorry, this is too sensitive, a circular or elliptical cross-section would develop and the spheres would come closer. And the distance by which the centers of the spheres come closer is called the overlap delta. And Hertz showed that the force, the repulsive force, because they have been squeezed, repulsive force would go as some constant to the power of this delta, not linear, but nonlinear. Sorry, there's a timer set here somehow. Delta to the power 3/2. So it's nonlinear. And this A, this quantity A depends upon the elastic constants, the Poisson's ratio here, sigma, and the Young's modulus. And 1 and 2 refer to the two different materials that can presumably come into play. So this is Hertz's law. Okay, Hertz's law basically says that the repulsive force between the grains is intrinsically nonlinear. And so the potential would be, instead of 3/2, this should be 5/2. So notice here that Hertz showed it was 3/2. That experimentally checks out as well. But when you look at the force, it's 5/2. And then you can write down the equation of motion for a chain of spheres, which is what we did. This delta is what if the spheres are pre-compressed. This pre-compression amount is delta. And then you have this rather awful nonlinear system. And because these are macroscopic systems that typically have some form of energy dissipation, one can factor it in by constructing a ratio of the unloading force when they're unloading over the loading force. And that's typically regarded as 1 minus omega. And this particular formulation was done by Otis Walton and Brown in 1986. There are more sophisticated ways of calculating energy dissipation, but we won't get into them. The basic idea here is that if you had a quadratic potential, which would be this dashed line, then as delta goes up, it'll go up like this dashed line. But if you have a Hertz potential, this blue line gives a softer potential at shorter range, a steeper potential at a slightly larger range. Thus, it's like a pillow that hardens very quickly. And so the contact time becomes finite. The system doesn't want to pay so much energy to remain in contact, and it disengages. And therefore, any kind of contact between two spheres happens over a finite time, and all energy transport must happen between this finite time, which is basically the reason why the solitary wave physics comes in. Although the solitary wave is actually quite wide. It's about 5 to 7 grain diameters wide in reality. But intuitively, the reason why the solitary wave comes in is because of that, because it's very expensive to maintain contact for long. The softness of this potential, therefore, determines how wide the solitary wave must be. And I'll touch upon that in a moment. So initially, of course, there were attempts made to use a continuum picture to see if one could explain what one was seeing. It turns out that if delta was small, remember, delta is this guy here, the preloading of the whole system, squeezing of the whole system. Imagine the system held between fixed ends and you're just squeezing that. That's delta. So if delta is small, the system is highly nonlinear. If delta is large, the system is weakly nonlinear. So if you have a large delta problem, the weak nonlinear case can sort of be shaped to a KdV equation Vitali saw, and he constructed a solution, but that had nothing to do with the physics that experimentally was seen. So clearly, this KdV equation picture turned out to be wrong, not the right way to go. The approximations don't hold up, in other words. The weak compression, which is the strongly nonlinear system, that gave this rather daunting equation, and it turned out that Vitali was more or less able to approximately solve it and show that a solitary wave, a soliton actually does show up. And that's in his book and many other papers he wrote. So I won't get into the analysis of this continuum equation, which is certainly a talk in its own right. But I'll talk about the whole problem looked at from the standpoint of particle dynamics simulations, which give a very different set of insights that you don't get from here.
So is this equation exactly solvable?
No, not exactly solvable.
But you said soliton?
Yeah, so basically this equation, Vitali dropped some terms, he modified it, and got it to a form where you actually can reduce it to an equation that is analytically solvable, and that admits a soliton. So that is what gave the understanding that this has soliton.
Okay, thanks.
Sure. So now let's go back to our more mundane model of actually having these grains held between fixed ends initially. And let's say we introduce a velocity perturbation at t equal to 0 at the extreme left end. And you will see that this velocity perturbation, which is a delta function perturbation, over time and space, actually over about 10 or so grains, it turns out typically for spheres, develops into this solitary wave. And the reason why I call solitary wave is because they do not cross as nicely as the total soliton did. Actually, they interact. They're interacting solitary waves, interacting solitons. That's why we call them solitary waves. And because it's a fully nonlinear system, it's very easy to use virial theorem, which tells you how much of a system at late enough times should be carrying kinetic energy and how much potential energy. So you can actually compute the kinetic energy of the solitary wave and show that the solitary wave carries that much kinetic energy, n being, let's just go back and remind you what n is. This is n. N comes from here. This is n. And the rest of the energy, 2 over n plus 2, is potential. So this carries potential energy, and it also carries kinetic energy. Of course, kinetic energy is more than potential energy in a nonlinear system. And that's why it moves, right? That's why it moves the way it does. It can move quite fast. And how fast it can move depends upon how large the perturbation is, which again fixes the system energy. And if you have perfectly reflecting walls, it doesn't matter. Because it has a spatial extent, it will hit one boundary and turn around. But the front end of it will turn around first, and the back end of it will turn around later. And so the wave actually must break down and reform. And that's fundamentally the reason why the scattering process is very interesting. As I told you, if you soften the potential, if you make n smaller or larger, then the solitary wave becomes, if n is smaller, solitary wave becomes wider. If n is larger, solitary wave becomes more tighter. And if n goes to infinity, it becomes 1 diameter wide. That's to be expected. So all that checks out nicely, which makes us happy. And this is the experimental photograph, if you will, of the solitary wave, now taken in terms of force and time, as recorded by a transducer. And this transducer is actually embedded inside a grain, right? The experiment was done by Francisco Melo's group at University of Santiago in Chile, one of my long-term collaborators in this. And this is the most beautiful picture of a real solitary wave that I have, that I can show you, excepting it's in force and time rather than the way I was showing you. So moving on, what happens if you turn this loading piece on, preloading piece on? Well, if loading piece is very small, you just get the solitary wave. Let me for now not go there, okay? There's a whole story with these little blips here. Let me not go there. Talk about useless stuff. This is really useless stuff. You actually get a solitary wave, very nice. Then you start to load it and things become really crazy. You get this long oscillatory tail. And initially the tail and the front of the wave are detached. But as loading increases, they begin to mix, so much so that ultimately the tail begins to severely interfere with the front, and it almost begins to look like an acoustic oscillation, although not quite so. If you look at the detail, you'll find that it's not quite so. Coming back to these blips are happening because it's a discrete system. So once you hit it, the particle goes and hits the first particle that's been hit goes and hits its nearest neighbor in the front, but then rolls back and hits the back end of the wall. So therefore, there are these minor blips that are generated, and you can see them in experiments as well. So let's cross these solitary waves. Let's take two guys from two ends and let's have them pass through and see what happens. So here we show This is the length of the chain. It's a long chain that we took in the simulations. Early time, late time, and we plot kinetic energy, and we have a, we have a solitary wave coming in from the left here, one from the right, and they meet in the middle at crane number 250 to be exact. This is 260, this is 240. And at this energy scale, notice the number here, not much of a difference, but now if you refine your scale, if you look closely, with 10,000 times more resolution, see what happens. They actually have scattering as they go through. As I hinted when I said that the solitary wave would hit a wall and the front would turn first and the back would turn later. Exact same thing. So we called them secondary solitary waves, and we reported them first in this 2000 paper, followed up with a bigger study in 2002. And it met with the usual resistance that, oh, you must have made a mistake. But then we had to fight and argue and point out that, no, look at our work and look at all kinds of cases we have looked at. And not long after, Francisco Melo's group from Santiago actually saw this, what we call secondary solitary waves. And let me explain very briefly Francisco's experiment. This is the granular chain. This is one embedded sensor. This is another embedded sensor. This is a striker that comes and hits here, starts a solitary wave that goes through, goes to the back, comes back. So if there is a secondary wave, then you should have a single wave going through and two waves coming back, at least, if you can see the first secondary wave. Now, I told you that this is 10,000 times more resolution in energy, right? So you shouldn't be seeing it. But clever experimentalists are amazing people. So what Francisco did was Francisco softened the back wall. This was a softer material. And by softening the back wall, he slowed down the solitary wave, thereby changing its energetics and thereby making the first secondary solitary wave much larger than what we thought it might be. And here you see, if you look at this particular inset, let's take B, you see that the solitary wave is going through the solid line. This is going from left to right. And from right to left later in time, you see a smaller solitary wave coming back. This is from right to left. And then you see the first secondary wave coming, which is here. And the second secondary wave cannot be seen in this particular study. There is more attenuation. So it was very clear proof that the secondary waves did indeed exist. The scattering was indeed real. And therefore, as these waves begin to break down, some kind of interactions between solitary waves should transpire, and that should lead up to what we were calling the quasi-equilibrium phase. Now, things just can't keep on breaking, right? I mean, if you start to break solitary waves, they become smaller and smaller and smaller. Soon you are left with no energy. That's not very smart. So there should be some processes by which energy not only goes downward as you have secondary wave formation, energy can also increase. So it turns out that when two big waves, one is overtaking the other, the bigger wave actually gains energy. When you have a small wave hitting a large wave, then the small wave is the one that gains energy, opposite direction. So there are all these balancing processes, and these balancing processes set the time scale. And eventually, the system goes to quasi-equilibrium, and eventually perhaps to equilibrium. So I'll tell you briefly about that as time permits. So this is, you don't have to look at so much. You just look at the first picture here. Let's not worry about all these details. Initially, what we are showing is time along the x-axis and the particle numbers along the y-axis. So there are about probably 25 particles in the system. And at the 25th particle, we introduce a perturbation. This gray scale that you see, it's kinetic energy. So initially, we introduce a perturbation. The perturbation generates a solitary wave, which of course runs back and forth. Every time breaking ever so slightly, these are hard balls. And ultimately, after many round trips, you see you get this very patchy, rough grayscale. That's your quasi-equilibrium, roughly speaking. So you do have almost no dependence or no dependence on initial conditions. You do have a Gaussian distribution of velocities. And at the same time, you don't have equipartition. That's what we call quasi-equilibrium. And these are the various realizations for various number of particles, odd number of particles, even number of particles, varying the small n, which is the force law, to different numbers. And you can control the rate at which the quasi-equilibrium is reached. You can even soften one wall, just like Francisco's experiment, soften a wall, slow down the wave, and that also gives you interesting journey. But we check for ergodicity. How do you check that? Well, we take something like velocity squared, we take a time average, we take a space average, and they both come out to be the same number to the precision that we can muster. Does that mean it's exactly ergodicity? No, but it gives a very strong hint that the system is likely ergodic. That doesn't necessarily mean that the system is reaching equilibrium or equipartition. So moving on, we looked at the fastest moving particle at any given point in time, which is this Vmax squared, the square of it, starting from initial time to many, many decades deep into the system's dynamics. And you see something very interesting. It has a Gaussian profile. Essentially, there is a fastest moving particle, but this fastest moving particle is barely different from other faster moving particles as time goes on, thus telling you that the system is headed towards some kind of a equilibrium-like phase. This is not terribly important right now, but we try to distinguish between what equilibrium might be and what quasi-equilibrium might be. And it turns out, as I said, in quasi-equilibrium, the system doesn't have equipartition. So this last line is most important. Dependence on initial conditions, of course, is not there in an equilibrium system. But in a quasi-equilibrium system, in most cases, it's not there, but one can arrange a little bit of it to be there. So it's a little bit more dicey. And in terms of ergodicity, generally speaking, they are ergodic, but there can be instances where they can be arranged to be non-ergodic as well. So they're richer, they're more generalized than equilibrium. One could calculate these kinetic energy fluctuations, as I told you, and one could also calculate how these kinetic energy fluctuations go down in time. When I say kinetic energy fluctuations, I'm really referring back to this figure, where the fastest moving particle's velocity square goes down. So kinetic energy fluctuation study idea came from there. There's a video theorem for you. Again, as a reminder, if you take spheres, kinetic energy is more than potential energy for the system, in this case for the solitary wave, and then for the whole system as such. 56% nearly kinetic, 44% roughly potential. One can at this time try out, because we are headed towards statistical mechanics anyway, a generalized equipartition theorem to see the end state. And you quickly see that generalized equipartition theorem, which I think was introduced by Tolman, if I'm not mistaken, in the 1920s, that the energy of the system can be thought about as this is the kinetic piece and this is the potential piece, which leads up to the Virial theorem, which shows how much of the energy is potential, how much of the energy is kinetic. As I told you earlier, no surprise. I'm just telling you something I told you earlier, just laying out how some of these calculations can be trivially seen because the system is fully nonlinear. The potential is very simple actually, even though it's not fully nonlinear. And ultimately, at the end of the day, if you know the energy, you can calculate. If you know the energy, you can calculate the specific heat, and you get a formula like this. You can also calculate the square of the kinetic energy fluctuations, and you get a formula like that. So these are exactly calculable. And this is very old statistical mechanics. There's nothing terribly new. Much of it goes back to the famous paper on ensembles by Leibowitz, Purkis, and Verlet in 1967. And there is some recent work also by a Spanish group. I forget the name of the group, which allowed us to do some of these calculations quite efficiently. This was part of Michel Zaborski's thesis at the time. Long and short of it is, if you look at the energy fluctuations of the system, you see it depends upon small n. It also depends upon big N, the number of particles. And so here we took two systems. One is for big N equal to 38. That's this one here. And the other is big N equal to 100 here. And we were able to calculate how that would, how the sigma k, the kinetic energy fluctuations, would change as small n was changed from smaller to larger value. It goes down. For both the small system case and the large system case. And you see calculations from analytics, which are here, and calculations from simulations, which are here, thereby telling you that things agree. And you can repeat the same thing for specific heat. Here, of course, there is no dependence on big N. Specific heat is specific heat. And the only dependence is on small n, and you only vary small n. Big N is taken to be 100 and 38 again. They sit on top of each other, as you would expect. And the CV turns out to be, as shown, the solid line is the theoretical line, and then you have the lines from simulations, thereby telling you that the CV agrees. If the CV agrees, that means the system has reached a full equipartition. Otherwise, the CV typically wouldn't agree. Otherwise, the kinetic energy fluctuations wouldn't agree. So what I'm trying to tell you is that the system actually goes from the strongly nonlinear phase, where you only have solitary waves, to quasi-equilibrium phase, to equilibrium phase. That's typically what we see. Any questions?
Yeah. Why it is an exponentially decreasing like function, CV, specific capacity, specific heat? Why it decreases? Because n plus 2 may cancel n, right? So it should be a constant.
Because n is very small here. So as n grows, it'll flatten out. Right, typical systems would have very small n, right? So therefore you see this. But that's a very good question, actually. I'm glad you asked that question. Okay, so I just want to emphasize, however, that this journey from to true equilibrium is incredibly slow. So the time scale of for this granular system for collisions is literally in the fractions of microseconds. Actually, even less sometimes. However, when you look at the time scale by which the equilibrium sets in, if you put in the numbers, is between 1 and 10 seconds. So you're talking 6 to 7 orders of magnitude. And we had estimated that there are at least 20 million collisions that must take place for the system to get to equipartition. So equipartition is a very elusive state that comes much, much later. But this quasi-equilibrium seems to be a very common state. And by the way, we have also seen it in the Fermi-Pascal system. I just want to tell you a few little things which are still in the useless knowledge phase. What happens as you study the dynamics of the system, fluctuations, for example, as you vary the preloading? So in the picture I show here, preloading, lowest preloadings we looked at on the left, highest on the right. And as you increase the preloading, what happens is that the kinetic energy fluctuations go down. Why? Because low preloading, strongly nonlinear, high preloading, weakly nonlinear, kinetic energy fluctuations will decrease. However, there is something anomalous happening. And this anomaly seems to be happening regardless of system sizes at a given range. And this range turns out to be when the magnitude of delta and the magnitude of this difference becomes comparable. This was a surprise. Nobody had ever reported this. We didn't expect it. We were just doing some sanity checks. And this is what we found. So this was in 2012, and this work was done now, quite a while ago. And this is in a paper that just came out in January. If you actually look at the kinetic over the total energy of the system, as I told you, kinetic energy is about 56%. So this is kinetic energy of the fully nonlinear system. For a harmonic system, kinetic energy would be 50%, right? So kinetic and potential are both quadratic, half and half. So as you load this system, the kinetic energy drops sharply, although it's a logarithmic scale, but still it drops sharply. And it turns out that when those two terms, meaning the preloading term and this term, they're competitive, you are smack in the middle around here. And this is a region where you have really, really, really mixed behavior. The system is actually still strongly nonlinear. And if you actually were to look at that energy zigzag plot like I've been showing you, again, kinetic energy in the grayscale, particle number here, time here, large system. No dissipation introduced. This is the case when you have zero delta, no preloading. This is the case when you have high preloading. So this is solitary wave-like. This is, of course, more acoustic-like, if you will. Smack in the middle, look at this. You have the entire quasi-equilibrium background, and you have stable solitary waves. Well, it's not super stable, actually. It's going down slightly in energy as time progresses. And we can calculate this exactly. And this shows up in this paper, which is published. There is a critical precompression at which you can show that the solitary coexistent phase of this solitary wave with the acoustic-like background comes in. To be brutally honest with you, this is a nicer picture. I don't know why it comes, but the guess is...
Excuse me, sir. I have in the previous slide.
Okay.
In the previous slide. What is L?
L is actually the preloading. It should have been delta, but I think at some point.
Okay, delta. Maybe, but it has a very low value, right?
Very low value?
Yeah, 10 to the minus 3, minus 5, minus 7.
Correct, and that's it. It is low. Actually, it's not very low in terms of grain compressions. It is low in terms of forces. So if you go back, let me quickly go back to here. When I'm showing you something like this,
okay,
this is already like 10 to the minus 2 or so.
All right.
So it's, okay, so when I'm showing you this one, this is where we were.
Yeah.
So that's actually the weak loading regime. And this is the strong, yeah. So this is the strong loading, this is the weak loading. And this one is around -5, 4, around here. So these loadings, by the way, are very easy to achieve in experiments. So I've had extensive discussions with Francisco on these loadings, and Francisco tells me that even if you want a 5 or 10% loading with stainless steel, we can do that. So the loadings that we are talking about are very, very weak loadings, and hence the regimes are quite nonlinear from that standpoint. Before I go to the real world in the last 5 minutes, the one possible clue I can give you why this happens. It turns out that the speed of the nonlinear wave and the speed of the background waves, they are almost the same for the system. It's almost like that condition allows for very weak interaction between the solitary wave and the background oscillations. We also, by the way, find that the width of the solitary wave and the typical wavelength of fluctuations in the background, they are also very comparable. So it's possible that the two are nearly transparent through one another, thereby minimizing scattering. But that's all we know. I mean, this is not an area in which we have been able to figure out much, although it's been almost a decade or more than a decade since we have first come across this effect. So what do we do with all this? Why do we need to know everything that we have learned? Rogue waves, of course, right? So it turns out that let's not take a very simple initial condition like a delta function perturbation. Let's say we rattle up the whole system by giving random initial velocities to every particle. It turns out that, not surprisingly, that the system would become very roughly in terms of all the particles are going back and forth, colliding with each other, creating all kinds of waves. They are interacting with each other. So if you forward integrate that in time, it turns out, not surprisingly, you find is what we call hotspots. So hotspots we arbitrarily defined as 6 times the fluctuation in kinetic energy. So typical fluctuation 6 times. You shouldn't have too many of them. But after long simulations, we find that even a linear system or a nonlinear system will have quite a bit of them. So there is nothing special about hotspots, nothing special when it comes to nonlinearity about hotspots. But now let us make this condition more stringent. Let us say that we don't want a single large fluctuation, but we want a series of large fluctuations all together. So it's like a continuous thing for a while. And we called it a rogue fluctuation, so as not to get confused with the rogue wave literature right now. This is again hotspots. These rogue fluctuations, actually, you can find. Whatever condition you set, you'll find them, more or less. But of course, if you make a very stringent condition, you may find very few of them. So this is the rogue fluctuation number, nr. And you can see this is log of nr. And this is, of course, the potential piece, n. And it turns out that it has this peculiar behavior of this. As n goes up, the system becomes progressively more nonlinear. The number of rogue fluctuations goes up rapidly. And if you turn on the loading, it gets killed off very, very rapidly because you see it's a double exponential decay. This is probably the first time in my life I've encountered a double exponential decay. We have done some more work on these rogue fluctuations. In fact, we have a paper that should be coming out soon in mechanics research communications on seeing these rogue fluctuations in the Fermi-Pascal system. But I'm battling it out with many naysayers, but it's close to getting accepted. Another very useful system, so to speak, you can take a granular chain and slowly shrink the masses. So it's like a what we call a tapered chain. I introduced this system in 2001, actually, in this paper with my students then. They're professors now in UT, University of Texas, El Paso, and Bob Doney, who works at the Army Research Labs in Aberdeen, Maryland. And what we found was that these systems were fantastic energy dissipators, and they're scalable. You can take them down literally to nanoscale, the particles, that is. This is one experiment that Francisco rigged up in Santiago in his lab. I took the photo. And it turns out that these are incredibly good energy dispersion devices. This is an experiment done by Masami Nakagawa from Colorado School of Mines and Huanagi at NASA Glenn, which is in Cleveland. And just with, I think, 8 spheres with a tapering of about 5%, I think, the force recorded at the tapered end goes down by 30% with 8 spheres. So that's quite a bit. And one can do enormously better. These are some nicer experiments Francisco group had published, where the force goes down from roughly about 25 newtons to about under 10 newtons. Not with too many spheres. I don't know how many spheres there are, but About 15, 20 would be the typical number. One can do much better by changing the designs, and this was Bob's work. And some of it we checked in experiments, but they were never published. They work very well, bottom line. And the last example is that you can actually take granular chains and you can constrain motion in them. And that gives you systems that are incredible sound filters, sound absorbing systems. Now, so we have written a series of papers with some more along the way. In this map, what you see is that this is the driving part here, amplitude. And this is the frequency of the actuator, which is this frequency here at this end. So it's basically vibrations being sent to the system. And what you see here is what comes out at the other end. And what comes out at the other end basically is nothing. Look at the decibels. So it's almost nothing. So it kills it off. It kills it off partly because these grains are frozen and these can move. There are other systems we looked at. For example, we looked at this two-dimensional system where you have a tapered chain and a flipped tapered chain. And this system also turns out to be a very, very powerful system, sound filtration device. And this system turns out to be not only a sound filtration device, but also a sound amplification device. And then this is a tapered chain, but it's flipped. So you excite at the tapered end, and these are heavier particles. This is a certain inhomogeneous design that is built into it, which is done by trial and error. And this paper is currently under review. Why is it important? Well, it's important because worldwide, 500 million people actually have hearing impairment. And if you want to go out to the store and buy something that gives you protection from heavy noises, you would be surprised at how expensive they are and how poorly some of them work. It doesn't have to be that way. You can take very tiny, small particle granular systems and actually do a fair amount of sound reduction, thereby protecting an enormous number of people around the world from eventual hearing impairment, especially in the high frequency end, which is where we tend to lose our hearing. I will not get into this problem, but back in the late 90s, early 2000s, we did a great deal of work on finding buried landmines using sound bursts. It's a three-dimensional system, not a perfect solitary wave, but it turns out that you can not only spot them under the soil, very shallow soil, a few inches. That's typically where landmines are buried. But you can also image them. So I won't talk about that. This is an image that we computed. And with that, let me thank you. This is a long slide. Let me move on from here. Essentially, you can find this is what we're trying to say. Let me finish with some observations. So I've told you about pursuing some useless knowledge initially. We talked about these Hertz systems. First, the Fermi-Pastor-Lamb system, then the Hertz system. And why the Hertz system? Because of the nuclear reactor problem. And then it comes out that once you begin to dig into the Hertz system, they have a lot of surprises for you. The quasi-equilibrium property, this non-integrability property that results in interacting solitary waves. And then if you examine them in the context of applications, you run into rogue fluctuations, you run into impulse mitigation problems, you run into noise dispersion problems, you run into landmine detection problems. We have also done some work on extracting energy from random noise, like road noise. I didn't talk about it. It's pretty messy. We published it, actually, with my former student, Saurish Chakravarti at MIT. So with that, these are the people who did the work. And thank you so much.
Thank you, Professor. Thank you.
Thank you.
Yeah, this forum is now open for questions, clarifications, doubts. Students, if you want, you can also put your questions in the chat box.
Yeah, absolutely. I know I covered probably too much.
It's a very good touch, Professor.
Thank you. Kind of you.
I have one more question.
Please.
The partial differential equation which you have shown, whether it has any name, like Bose-Stake equation.
I think this is Nesterenko's equation, they say, I think most of the time. So this particular equation, Vitali introduced this in 84, 85. And he has a book. There's a book that he wrote in 2001. It's called Dynamics of Heterogeneous Materials.
Okay.
It was published by Springer. And he has a newer edition. I think it came out in 17 or 18. So in that book, the first chapter is dedicated to this entire topic.
I see.
And many of our works are also included in it, but not quite to the extent I covered today. So in that book, he actually discusses constructing the solution.
Okay.
So you might be interested in that.
Yeah. So did you try other kind of solutions for this kind of problem? You look only for solitary wave type or other type of solutions also?
It's a fantastic question. So in 2001, I didn't mention that paper. In 2001, we actually wrote a paper. It was myself and my former student, Marian Manciu, in PhysRev E, in which we took the discrete system, and we assumed, of course, that there's some level of stationarity. So you can relate the distance to time. And by putting it in, we managed to construct, again, a solitary wave solution, but it's enormously better than Vitali's solution because it is able to actually capture all the properties that we saw in the simulations. So in terms of solitary wave solutions, we have improved on Vitali's solution in that one. So that's number one. Number two, there are only two possible things that happen when you simulate them with a velocity perturbation. Either you get a solitary wave if there is delta equal to 0, big delta, or if big delta is finite, then you get a solitary wave with a tail, as I showed. So let me show you again. Here. You get the tail, right? So we tried to actually construct a solution for the tail part. We wrote this paper in a European physics letter issue in 2017. It was Wesley and me. Wesley was my former student also. And we were able to show that this basically has a Bessel function-like behavior. And if you couple the Bessel function-like behavior with the solitary wave behavior in our 2001 solution, and then allow for a way to fix the distance between the two by hand, then it turns out you can not only capture this behavior, but you can exactly capture behavior deep into the quasi-equilibrium phase by integrating that solution forward.
Oh, I see. Interesting.
Yeah, so it told us that it needed some fixing because how much of this and how much of that you want is needed. But if you move it forward, once you have matched it, let's say with the simulation, and know that you are more or less correct, then if you simulate that solution forward, you get the quasi-equilibrium phase and the equipartition phase. Everything falls off almost in toto with simulation. So that was very satisfying because that told us that we were on the right track. But anything beyond that, we haven't seen or tried, because anything beyond that would probably be better done with different initial conditions.
Okay.
Right? Because we took the simple velocity, delta function, perturbation. Different initial conditions would open up a lot of different issues. So yeah, but that's actually open game. I mean, for example, suppose what happens if you introduce some kind of an n solitary wave as an initial perturbation? You'll probably start seeing rogue fluctuations. But that would be terrific. But we haven't done that.
Good, very interesting, sir. Very interesting.
Thank you.
Students, any questions?
I think students got worried about this.
Yeah. Sometimes they may hesitate to ask.
I know. I was a student also at one point.
Okay.
Many years ago.
Yeah. So since there are no more questions, I would like to conclude the session. So I would like to conclude the session by thanking Professor Sen for accepting our invitation and giving a very, very interesting talk, on solitary wave dynamics in various kinds of chains. Thank you, sir. Thank you very much.
Thank you. You have a great day.
I'll the other details. Yeah. Thank you.
Great evening, actually. Yeah, daytime here. Bye-bye.
Yeah, when you come to India, please visit us.
Yeah, we'll try. I'm going to be in Jodhpur. I have a visiting appointment in Jodhpur.
Yeah. There are a couple of conferences coming this year in India on nonlinear dynamics. Yeah,
I saw that. I usually go to the this nonlinear dynamics conference series.
Yeah. Okay.
So this year I won't be going, but yeah, it'll be terrific. I'll definitely be in touch, and please you be in touch as well, and keep me in the loop of these emails. I'd like to attend the talks. All right. Thank you.
Thank you.
Bye.